Okay, cool. So yeah, Ted just gave a little bit of a preamble, but we're into the deep learning section of the book now. So we did all of the sort of fundamentals of machine learning, how you set up experiments, how you train some linear regression and SVM and decision trees and that stuff. And so now we're finally evolving into deep learning stuff. So this is the stuff that everyone's excited about recently. So all of the big fancy models, we'll start learning about them. Um, so I'll start us off just talking about some of the concepts that we'll be touching on throughout this chapter. So artificial neural networks, perceptrons, backpropagation, activation functions, multi-layer perceptrons, the sequential, functional, and subclass APIs in Keras, TensorBoard, hyperparameter tuning, if you take away those key concepts, if you're at least like somewhat vaguely familiar with those concepts by the end of the chapter, then that's really what you need to capture. They talked about a whole lot throughout it, and there's I think this was one of the longest chapters in the book, so there was plenty of stuff in there. But if you just kind of understand those concepts, you'll do well. Um, so I'll start with just a little bit of history about the artificial neural networks. So they originally came as sort of inspiration from the biological systems. So in biology, you have these neurons, and what people have found is we have this like emergent intelligence. You have these little neurons that don't really do that much, but then when you compose them all together, you get really complex intelligence, and you can pick up patterns, and you can recognize a cat and stuff like that. Um, so the artificial neural networks came inspired from that, but we've slowly diverged further and further and further. When I was first starting, my first boss, he was a researcher, and his whole thing was spiking neural networks. So it was even more closely related to actual biological neural networks. But that whole area of research has kind of just died off because um, it's one thing to kind of simulate the biological process, and we found that we can do just as well without actually needing to kind of mimic that. um, so with artificial neural networks, we do kind of the same core idea though, of having basic units and then scaling them up and having them all interact so that we can get various different properties. um, so the first part that we'll start with is with these neurons. Like I was saying, an individual one, it's just like maybe a threshold function. It's just saying, is it above this value? Is it below this value? But then when you start composing them, you can do various different things with them. So with just a single layer, you can represent stuff like and, or, and not. So you can kind of make the different logical things that you might be used to. Um, so that's a great start. But if you only have one layer, you can only represent so complicated of patterns. So this is what most people would call a perceptron. And so the basic idea here is we have various different inputs. So like if we look at x1, x2, x3, those are different variables. And then you have weights, and these weights are they're multiplying to the x1, x2, x3, for example, and then it's going into a step function, or we would call it an activation function now. Um, and so this can represent some different functions, but it's fairly limited. If you look at this is kind of just linear regression with an extra function at the end. Um, so you can't really represent that complicated of patterns. And so um, what people have figured out is you can actually stack these up. So this is just a simple perceptron, just a single layer, single set of weights. And then what people figured out is you can actually um, have, I'll take a step back. So we can have in this setup, we have a single output, but we can also have multiple outputs doing multiple different things. So you might have two inputs and three outputs, and your outputs could be mapping to different things. So you might be predicting, I don't know, house price and whether it's a home or a business or some other thing. You can have multiple different outputs. Um, and so with that, what people realized is if we can make it have multiple outputs, what if we put that output into another perceptron, and you just kind of stack them together. And with that, you can represent even more complicated patterns. So one of the famous ones here is the XOR. So this is a simple example that they put in the book, basically saying with simple perceptron, you can't actually separate all of these points out. So if you wanted to separate the red triangles from the green squares, you can't do that with a perceptron. There's just no way to draw a decision boundary with those weights in order to do that. But with the multi-layer perceptron, stacking them together, you actually can. And so this diagram on the right is showing that premise. We still have the same two inputs. So we have x1, x2, and then we have some weights. So all of these ones, they're just passing it through. And then we have these units here, and these are doing their thresholding. And then after that, we can combine those outputs again in the next layer. And so those get another weight, -1, 1, and those get added to this final layer, and then is thresholded again. So with this, we can stack our perceptrons together, and then we have a deeper network, and then we can do much more expressive representations. We can represent more functions and stuff like that. So the core idea, we have perceptrons, which is like your single layer, and then you have multi-layer perceptron, which is saying we can stack multiple layers together. In previous chapters, we've talked about SGD and batch gradient descent and all of that stuff. So that's how we would update the weights for these. So the general idea is we're still doing backpropagation. We've mentioned that in previous chapters, in order to try and optimize these weights. And the way that this works is you run your predictions through your network, you measure how good is my model, how much loss does it get, and then you go backwards and you say, how do I adjust all of these weights in order to make the loss go down? So imagine we're going through this network and we're trying to predict something, and we go, oh, it's predicting a little bit too high. Then you have to go back through the network and say, how do I adjust these to make the prediction a little bit lower? Given whatever input I had.
Just a quick comment. When you read a chapter like this that's talking about the origins of deep learning, people usually always start with the perceptron. And the perceptron, from a historical perspective, is a very specific design of a neural network. And you see in the drawing, in the blue circle, it's got the thing that looks like a stair. Okay. And in later diagrams, you're going to see it has a curvy shape, more like an S in the middle of there. Okay. We do not use the exact historical perceptron anymore. Okay. And the multi-layer perceptron, MLP, that term still sticks around. I say MLP pretty much every day, but we're not technically talking about multi-layer perceptrons. We're talking about multi-layer neural networks. And just for historical reasons, people get sloppy. And so just so you know, today you will pretty much guaranteed never see an actual perceptron. So if you hear anybody say perceptron, neural network, MLP, anything that sounds anything remotely like a neural network, they're really talking about the modern thing, and they're never talking about the original old thing. Okay. So it's useful to just know from a historical perspective, but don't get confused by the terminology. Anything that you see, like Facebook is using something, believe me, it's a modern one. It's not the old one.
Yeah, good point. There's a lot of different acronyms that people kind of use sloppily together. So MLP, one of the ones that I've heard a lot recently is FFN, feed forward network. Artificial neural network, they might just say neural network. Like, they all kind of map to the same thing. If you really dig into the definition, they do actually have some nuance there, but people just say them interchangeably. Yeah, good point, Ted. So with these extra layers, what people have realized is that if you do just this basic setup, so you say, I have multiple layers in my neural network, and then I just run them, and it's summing these results and applying the weights. You can represent more complicated relationships, but there's a limit to that. It's still linear in some way. And so what people figured out was if we apply some activation function, then we can also do nonlinear relationships, which opens up the world of what we can do a whole lot. So that's what we're seeing here. So like Ted was mentioning, this is the step function, but some of the common ones that people use now, ReLU, TANH is not as common anymore, but sigmoid, there's a whole different family of activation functions, and this is basically just ways to introduce nonlinearity into your neural network. You want kinks in your graph so that your model can move things around and make nonlinear representations. If you didn't have any, then it's just kind of shifting and tweaking your values around rather than actually being able to stretch them out and push them across different thresholds. So here's the multi-layer setup. So we have two inputs, X1, X2, and then one of the interesting points with this is when you start doing multiple layers, you can have an arbitrary number in the middle. So before we were limited by you have a certain number of inputs and you have a certain number of outputs. So that's just the definition of your network. But when you start adding these hidden layers, you can say my inputs are going to map to 500 middle layer or 500 middle neurons and then go back down to one final classification. So what people realize is you can start with just two variables, but then you can blow it up to 500 neurons and you can get really granular look at all of the different relationships there. And you can even add more layers. So right now, this just has one hidden layer, but you could have more and more and more. And so you could do even deeper, more nonlinear relationships. So here's a little diagram showing some of the activation functions. So they have this one that we don't use very much anymore. ReLU is very common. So that's this pink one that basically just says be at 0 until you're past 0, and then it's just linear with whatever the input was. So if it's 3, then the output is also going to be 3. If it's below 0, then it's going to just be thresholded at 0. So the way that it's nonlinear, it's just a threshold. So ReLU is very common because it's so easy to compute. It's basically, if it's below 0, just set it to 0. If it's not, then just pass the value through. Yeah, you got a question?
Two quick things. So ReLU is basically a step function.
I don't know that I would call it a maybe a step function. I think of it just as a single threshold because you don't have multiple steps. You just have an individual threshold that you're stopping at, and then beyond that, it's just passing all of the values through. So it is technically a step function, but it only has one step.
Okay. And the other question is, and I apologize because it's a little bit late, but when you create these middle layers, are you actually creating lots of new features, like maybe combinations of the data in new ways? So, it's, I guess, going back to the example before, it's, long petals plus tall plant plus this equals one cell, and then some other combination is another cell. Is that one way to think about it?
So the way to think about it is that the model is learning those relationships on its own. So there's one way of doing things where it's like I have these inputs and then I want all of the interactions of these inputs. So you could say like in one setup you could say I have the length and the width, and then I also have length times width. You can represent something like that inside of the layers of the neural network, but it learns it itself. So you don't have to actually say like do all of the interactions, do all the powers of, and so the neural network is learning that itself. So you don't have to actually define it. It's figuring out what is useful in order to predict my goal.
But just to think about it conceptually, is it like it's coming up with a whole bunch of new features based on the combinations of the old features, and is that a proper way to think about it?
Yeah. Yeah, so it's looking at the interaction of the features to generate new ones. So the way that I would read this, imagine we have our two variables. It's finding many different ways to interact these variables. So here's one set of interaction, another set of interaction, another set of interaction. And so now we have four different variables that are some weird interaction between the two input variables. So now we have a deeper representation of X1, X2. So it could, in theory, just do something as simple as saying, I actually want this neuron to just be X1. I just want to keep that variable. That was a useful variable. So it could say this variable is just X1, this variable is just X2, and then this one is some weighting between X1 and X2. This one is another weighting between X1 and X2. So it can compose them however it decides is valuable. So yeah, focusing on the activation functions, we have a lot of different possible activation functions. Some of them are kind of situational, like you want them at the end of your neural network or you want them in the middle. So there's many different variations on these. In practice, they have some impact on your neural network and its performance, but in general, like if you just said I'm going to put ReLU in the middle, it's not going to be the difference between it converges and it doesn't converge. It's just maybe they found a new way to do the scaling of this, and then it converges a little bit faster or something like that. But it's not going to be the difference between it works and it doesn't. So they also show the derivatives here. So this is very important for when we're doing the backwards pass. We want to say how much do we change the values in respect to all of these other values, and so the derivatives are important for that backpropagation step. So one of the things that they point out is that in ReLU, it's actually undefined at 0 because it suddenly goes from 0 to some other value. But in practice, we just leave it as 0, and then that's just good enough. There's certain edge cases like that where in practice, you never even run into it because it's just a default that works perfectly fine. Yeah.
Thank you. I'd like to build a little bit. Whoa, sorry. I'd like to build a little bit about the layers conversation we were just having. So when we're talking about how at each layer, like essentially features are being created, and then at the next layer, we are identifying relationships between those features and then creating new features out of them. So when that is happening, are those features that were created from the previous layer being like deleted or replaced by the new features? Or are the new features building on top of the features that are already being generated? Does that make sense?
Yeah. So they're being built on top of the previous features. So the way that we can look at this, so working through this whole graph, we have two inputs. We have X1, X2, and this first layer is saying find interactions of those features, basically. It's saying what is useful between X1 and X2 in order to predict my goal. So we have this middle layer now that has interactions between X1 and X2. And then at the next layer, it's saying, what do I do with all of these interactions in order to make my outputs? So we have interactions here making some intermediate features, and then those intermediate features are being used again in order to say, how do I more accurately predict my final output? And that goes when you stack more layers, it's just saying interactions of interactions, interactions of interactions, just keeps going.
Okay, but is the initial interaction between like X1 or X2 or whatever, is that being used in the input, or has it turned into something else at that point?
It's being reused. So it's being passed through the network. So at this point we have the inputs, and then at that point we have the intermediates, and the intermediates are what's being passed to the next layer. Yeah.
Thank you.
Yeah, so just quick comment. I mean, at a given layer, you could it could be that the model learns to take 1 times the input from one of the earlier layers and 0 times all the others, in which case you really are just keeping it alive and passing it on. Okay. And we'll see in later chapters in discussion that you could actually have a design that's different that actually lets some of the earlier ones just skip around the later so that it explicitly is not having to learn that pattern just to keep it alive. So it's kind of an interesting question. But at this stage, for just the first chapter about neural networks, if you just have the big picture that they're learning features and new complex things that help you solve the problem, that's probably just good enough at this point.
Yeah. So the way some people looked at neural networks for a while was automatic feature engineering. So like to the question that was asked before, like you can manually define all of these interactions, or you can say neural network, you figure it out. What are the useful relationships in order to get the most accurate output? So there's that was a common way that people described it. I think they don't say it's typically like feature interactions that much anymore. So now we'll look at code just for a second. So they showed this example of Scikit-Learn, and what they're doing is they're loading a California housing data set. So this is a common one that people use in order to just practice different algorithms on. They have their root mean squared error, they have their train test split, and then the part that we're really focusing on is this MOP regressor. So this is that neural network that we just defined before. We're saying, how do we make this with Scikit-Learn, basically? So the idea here, we load in our data set, we have housing data, and so this comes with 2 different pieces. We have the actual data, and then we have the target. So the housing data has different variables on like the number of rooms and the square footage and stuff like that. And then we have the target, which is saying what's the price of the house. So they split it into train and test, and then they define their MOP regressor, and they're saying, I want it to have 50 neurons, 50 neurons, 50 neurons. So at the input, it has however many variables, and then it has one layer with 50 neurons, and then another layer connected to it with 50 neurons, another layer connected with 50 neurons, and then it goes to the output, which is just 1. We're just trying to say, what's the price of this house given certain variables? So we defined our model, and then we say, pass the data through it. So we say, give it X train, and then try and make it predict Y train. And then what it will do is it will do a bunch of training. It's looking at the data, making predictions, and then updating its weights in order to try and optimize those predictions. And then at the end, it's going to try to make predictions on the new held out X valid data set. So with this many lines of code, you can train a neural network. So most of this is actually data loading and import. So you can see how easy it actually is if you want just MLP. So with this, they say we get a RMSE of 0.505. I don't know exactly what the units are on that, but yeah, you can see out of the box, pretty easy to do. So that's the Scikit-Learn version.
Ryan,
Yeah, go ahead.
what is the activation function they have used in this MLP regressor? Have they mentioned it?
So in this, there's no activation function.
So is this like a linear they have put it, or?
I think, hang on, Ted's correcting me. I think that it does actually have ReLU inside of it. So it doesn't have an activation at the end because it's just outputting a raw numeric value, but inside of it, I think it does actually have ReLU. That's probably its default. And I think that that's something that we can define with the MOP regressor. We can tell it which activation function to use, but its default, I think, is ReLU, like Ted's saying. Does that answer your question?
Yeah.
Okay. So that's the basic Scikit-Learn setup. And so one of the things that I wanted to stress on is the the way that I think about the different model types, I mostly just associate them with different activation functions. So like the one that we just looked at, that's regression. It has no final activation function because it's just saying output any value. If it's house prices, it can be 100,000 to 100 million or something like that. So it needs to be just unbounded. It can be any value. And then for binary classification, so you're just trying to say like, is this going to happen 90% likely, 10% likely? Then you apply a sigmoid activation function at the end. So that's squishing it down to between 0 and 1. And you would use a loss function like binary cross entropy. For multi-class, so this is one where it's like I have 10 different options and I want to pick one of them. You would use something like softmax. And so softmax is basically saying out of all of these possibilities, make them add up to one. So it's going to be 70% likely this, 20% likely this, 10% something else. So this is saying I have 10 options, you have to pick a single one of them. So in that case, you typically use softmax and you use something like categorical cross entropy. And then for something like multi-label, where you're saying it can actually be multiple things. So they showed an example where it's like an email can be classified by, is it spam, not spam, but it can also be classified on, is this related to business? Is this personal? Is this something else? So you can actually label it for many different things and it's overlapping. So in multi-label, you would typically just say like, this is a bunch of binary things. So you can just use the sigmoid again. So with this, you say I have 10 different things that I'm checking for, and each of them can be yes, no independently. So you're not saying it can only be one of these options. I see a request for the notes. I'll drop these in the Zoom.
While you're doing that, I'll add a quick note. I really like the way, Ryan, you just explained this, and I'm jumping ahead a little bit, but kind of stalling while Ryan does that. Later on, when we talk about Keras, the book sort of covers the same thing that you just did, but I think you did it better than the book. One of the things that really confused me when I first started learning neural networks and started using Keras is wonderful in that, like, you just say to a certain degree, give me a neural network, and then it has some parameters, and you just pass it in, like, my inputs are going to be this, my outputs are going to be that, and like my loss function is going to be this. But then when you go to the documentation page and it says there are 20 different loss functions, it was very, very mysterious to me which one. And it was even more confusing because, like, you said we want cross entropy for multiple class, but they have different versions of it depending on whether your 10 classes were the actual integers 0 through 9, or whether your 10 classes were a list of 10 numbers 0 or 1. And anyway, I just didn't think it was explained super well. So I just wanted to note that this is like a little bit of a tripping point. The beautiful thing about Keras is that it kind of does everything for you automatically. But the bad thing about that is that you don't actually see what data is getting passed into the loss function. You don't see what shape it is. You don't see if it's floating point or integer. And so that actually kind of made it a little bit harder for me at first, because it was kind of like black magic for me.
Yeah. Keras is very nice because it abstracts a lot of the details away from you, but then sometimes you don't know what's actually happening. And the danger of that is, with a lot of neural network stuff, it doesn't just outright fail. It's not like, okay, the code's incorrect, it won't run. It's like, this isn't converging. Why is it not converging? Why is it getting 30% accuracy instead of 90% accuracy like I expect? So with neural networks, you can fail in really strange silent ways. And if you aren't like tracing through all the details, you don't know exactly why that might be happening. So jumping into what Keras actually is. So Keras is this really nice deep learning library. It originally started as sort of like a nice wrapper for a lot of the different neural network training setup. So Cafe and Theano and stuff like that. And then eventually it kind of converged on TensorFlow. And then eventually TensorFlow just absorbed it. So Keras is this nice wrapper around TensorFlow now that basically gives you some different ways to define models and train models. So I'll touch on there's three different major ones. So there's the sequential, there's functional, and then there's subclassing. And I'll start us with this sequential because that's the easiest one. So following with what we were training before, this is very similar. So we're just actually defining the layers now. So the MLP regressor before, we said, I want it to have 2 layers of input, and then I want 50, 50, 50 intermediate layers. This is very similar. So they're basically saying, in this, they were looking at the fashion MNIST. So it's actually images. And they're 28 by 28 little images showing a purse or some shoes or something like that. And then what they're doing is they're flattening it. And then they're saying, okay, do 300 neurons, then 100 neurons, and then 10 neurons. And then that's our final classification. So we're classifying into, yeah, go ahead.
What does it mean to flatten it?
So the flattening it right now, the input is 28 by 28. So that's the height and width of the little image of the purse or the shoes or whatever. So it starts with height and width. And then when you pass it to the neural network, it ends up something more like this, where you have x1, x2. So what they're saying is basically 28 by 28 becomes just one flattened vector. It no longer has height and width. And that's just a constraint of the way the layers are set up. It just assumes that it's flat. It assumes that it has one dimension instead of 2 dimensions. Yeah, so that's this flatten operation, and they could have done this outside of Keras. It's just easy to flatten it to 1D inside of Keras, so they just did it that way. But if you had 1D input, you wouldn't need this. So it takes the 28 by 28 input, it flattens it to 28 times 28, so just a single dimension, and then that is going into 300 neurons, and then that goes into 100 neurons, and then that goes into 10, and we can see they define the activation functions here. So they say ReLU, and then at the end they say softmax. So what we were talking about before, when you're doing pick 1 out of the 10 classes, you use softmax because that's going to constrain it so that all of the outputs sum to 1. So then it becomes sort of a probability again. So this is the nice sequential setup. But we'll see in the later sections, the difficulty with this is not all models are just basic sequential. You're not just saying, here's my input, next layer, next layer, next layer, next layer.
One quick question. Can you scroll up a little bit? Yes, here we have 3 different dense layers, right? 300, 100, and 10.
Yeah.
Are there any logic behind choosing this number of layers, or what is the logic behind that based on the different data set?
Yeah, so for this, it's just arbitrary. They're just using it for an example. In reality, if you have enough capacity, you don't really have to worry about the numbers too much. And when people are training small models like this, it doesn't really have that big of an impact if you set that to 30 instead of 300. So in this, it was just arbitrary. Like, people do have strategies for picking out what's the optimal size for my neural network, but typically when someone's trying a problem out for the first time, you can kind of just say, set it to some small kind of reasonable value, set it to 100 or something, and then just run it and see how it performs. And then if you want to, you can say, okay, now run it with 1,000. Does 1,000 do any better? If it makes no difference, then you just probably stick with the smaller one.
Gotcha. Okay, thank you.
Yeah.
Ryan, to the question that he was asking, I want to ask that is there any strategy to decide number of layers and the parameters in it? Is there any strategy people now follow, or just their gut feeling they do by their experience?
It all depends on the data and the problem that you're trying to solve. So in my experience, actually fiddling with the number of layers and the number of neurons is not the highest value use of time. So people do have, like, people have researched a whole bunch the different strategies for what's the optimal, and we'll talk a little bit later about some of the like automatic methods you can do to try a bunch of different options. But in general, I would say pick some kind of just reasonable ballpark somewhere between 100 and 1,000, and you'll probably be fine as long as it can fit on whatever hardware you're running it on. Then you're probably doing all right.
Yeah.
Yeah, I'll
makes
just add a
sense.
quick comment. I think it's probably going to come up in later chapters, but when when neural networks were sort of fairly new in their resurgence, like in the whatever late 2000s or something like that, people were worrying about how do I build a network like this and how many layers and how many units should I have in layer 2 versus 3 or whatever. These days, if you're working on something with a neural network, it's probably a hard problem. And if that's the case, then there are usually other people who have worked on similar problems and they've already done a lot of testing. And so most of the time you're just saying, like, let me start with Bob's repo on GitHub, and it already has a design, and you're not, like Ryan said, you're not necessarily really going to get much difference in performance by tweaking it. So it's covered in the chapter, but the reality is it's not, in my opinion, not really a thing people do.
Yeah.
Got it.
So in my early days doing Kaggle competitions, this was something I messed with a lot. I would rerun the model and say, try this different dimension, try more layers, try different neurons. And my conclusion after all of that was I never saw someone ever win a competition because they said, oh, I got exactly the right number of neurons or the right number of layers. Like that it does have an impact on performance, but it's not nearly as important as like getting your data right and training with reasonable values and just iterating a lot. So yeah, we'll talk about it a little bit more in the hyperparameter tuning section, but I would say in general, don't stress about it too much. Yeah, is there another question online?
Yes, got a question. So, and it's something that was stated in the book, but you said it in a different way. So, in the code you said before, when we have to flatten the curve, we have to flatten. That takes away dimensionality, if I'm understanding that right, or I might be off. But in the book, it says Keras needs to know the shape of the inputs so they can determine the shape of the connection weight matrix of the first hidden layer. And at first, I had a question about that. Is that 2D or 3D? But you're saying it doesn't do that at all? So I'm kind of confused.
So in Keras, it's nice because it actually infers a lot of the shape changes that you need. So in this, what it's saying is it's saying the input shape is going to be 28 by 28. And then this flattened layer is saying take it from 2D 28 by 28 to just 28 times 28 on a single dimension. And then all of these dense layers, it's automatically saying, okay, it was this value. What do I need to do in order to make it 300 and then to change it to 100 after, to 10 after? So the way that Keras works, you do tell it the shape and then some of the operations, and it figures out the in between steps.
Okay.
Does that answer your question?
Kind of, sort of, yeah. Thanks.
Yes,
Yeah.
if I can add a quick comment. The layers that we're using here, dense layers, they only accept one-dimensional input. We're not going to talk about batches for the moment, but for your regular data. So you can't pass it in a square that's 28 by 28. You have to pass it in just a one-dimensional, I think, what is it, 784, whatever 28 times 20 is. So you need to pass it in just a single dimensional 784 long thing of floating point numbers. Later on, we will see other kinds of layers that maybe can accept square or other shapes, but this one has to be 1D, and that's why you either have to manually, like in your data before you send it to the neural network, Ryan said, you could just manually change it to a single 784 list type thing, or you can do it inside of Keras and TensorFlow with the flattened layer, which basically always squishes it down to just a single dimension.
Could you went through about half this already. So we have the sequential, we have the input, the shape, the flatten. What does it mean when you say when you're adding 300 and then you're adding 100 and then 10? What exactly is it doing?
So that's adding the different layers of neurons. So the way that I would match this to this graph is say, okay, our input shape was 2. And then at this point, they're saying add 300 at this layer. And then they're saying add another one, and this one has 100, and then 10 after. So it's saying each of these is the next layer. So these values are getting passed to the next layer, which is going to have 300 neurons. Yeah. Yeah. Yeah.
So based on my understanding of photos, there's a lot of the spatial relationship that's I would assume is lost and would have to be relearned when you go from the two-dimensional to flattening. Does that have a significant impact on the amount of time it takes to train, or like what is the impact of that?
Yeah, so we haven't talked about it too much, but if you think about what this is doing, we have an image that is a square like this, and then when we're flattening it, all of a sudden you don't have any spatial information. You don't know this pixel is next to that pixel, for example. So it does actually really hurt the learning process, because now it's saying, look at every pixel kind of individually, and then say like, oh, the top left pixel is red, so that must mean there's a cat in it or something like that. So doing it in this way is not the way that most people would recommend it, but they're just showing like, here's how you set up the neural network. So we'll the later chapters we'll talk about convolutions and stuff like that, and that will actually look at like, here's a window of pixels that I'm looking at all at the same time, so I can say like, this little window has fur in it or something like that. But yeah, so that's a good point. This really hurts the learning, because it's looking each pixel individually and it doesn't really know its positioning or what's around it or anything. Yeah, so flattening it, you lose a lot of information.
What about if it's a 3D, structure? Will they still flatten it? They have to do it for this particular.
For this specific setup, yeah. So flatten will just take whatever you have and just crush all of the dimensions down to 1. So if you have like a 3D scan or like volume data or something like that, it has more dimensions, or you have something that has time with it as well. Like you have all these extra dimensions, you can just say squish it and make it a single flattened dimension. That's what this will do. So that's not necessarily the best way to process things, because typically you want your time axis to be handled different than your height and width, for example. But yeah, so this flatten will just crush anything and just make it one dimension. Okay.
Hey, Ryan, this is Stephen. Following up on a question that you were answering earlier. So we have 784. So we flatten the 2x2 shape into a single vector of 784. But the first layer is only 300. So this is a situation where we have less nodes in the first layer than inputs. So help me understand, how do we line them up? So is each node then of the 300? So I guess what I'm struggling with is, why isn't there 784 in the first layer, right? So it's a 1-to-1, right? And you have a like 1-to-1, or not 1-to-1, but 1 to 784 for each of the inputs. So what happens when it's less than? So I now have 300. So does that mean I'm having trouble reconciling that from a sort of from a graphical perspective, right? So if I had 300 of, if I have 784 X's, but only 300 in the first hidden layer, how are they being linked up?
So the way that this actually works, I keep pointing to this graph. I wish I had one with more neurons on it. But so in this setup that we were looking at before, it only had two input neurons. So if we look at this, we have X1, X2, and then the part that we're talking about there, the part that's going to 300, is actually this middle part.
Right.
So we
Yep,
have
got that.
1,
Yep,
2,
yep.
3, 4. And so to map from 2 to 4, we actually have connections going to all of those 300. And so we can do that for an arbitrary number. We're just basically saying, okay, we start with 784. Those 784 are getting weights to 300. So it's getting reduced in that way, but the number of neurons doesn't have to match the previous layer, because the Keras is doing this nice thing where it's saying, okay, what shape weights do I need to go from 300 or from 784 to 300?
Okay, so I think I've answered my own question in what you just said, which is, so in that particular, if you can go back to the diagram really quickly.
Yeah.
So in that particular case, let's pretend that there were actually 8 inputs, like double the number of the first hidden layer. So it'd be X1 through X8. So all that changes is that basically each one of those 4 nodes in the hidden layer, each one of those neurons, would be actually connected to 8 from the input layer, right? So there would be 8 weightings for each one of those neurons.
Yeah, exactly.
Gotcha. Thank you.
So that's one of the things that Keras hides from you. So if you were to do this manually, the difficult part is actually in, if you go to PyTorch or raw TensorFlow or some of the other training setups, you actually have to define both. You have to say, what's the input size, what's the output size, and that can get very annoying because you say, okay, this one went up to this dimension and then down to this dimension, and I need to keep track of both shapes on every setup. Keras does this nice thing where it just infers, I know it's going through this path, so what size matrix do I need at all the different places in order to figure that out? So the kind of hidden thing here is we're saying 300, but in PyTorch or something else, we would say 784 in, 300 out. That's the way that we would define it. So you would have a bunch more shapes here. So we would say 784 in, 300 out, and then 300 in, 100 out, and then 100 in, 10 out. So we would have to actually define the shapes at all of the different places. So Keras is very nice because it saves you the headache of needing to define all of those numbers. And it's especially hairy when you start doing convolutions and LSTMs and all these other things that might change the shapes in various different ways with padding and max pooling and stuff like that. So Keras is very, very nice for that stuff. So one of the nice things that Keras has is it has this summary function. And what this can do is basically I define this network and then show me the path through this whole thing and show me the number of parameters and the shapes at all of the different places. So like in this, we can see the flatten was taking our 28 by 28 and turning it to 784. And then our dense is going to 300. Next dense is going to 100. Next dense is going to 10. And then we can see the corresponding parameters. So the parameters in these case are all of these connections. So it's saying to go from 100 down to 10, we need 1,010 parameters. So this is 1,000 for the weights and then 10 for the biases. And they also show you the total number of parameters, how many megabytes, gigabytes, whatever your model is. And then they show you the number of trainable parameters. So one of the things we'll learn in the future is it's pretty common to have something where it's like someone trained this amazing model. Now I just want to tweak the last layer or something like that. So you can say freeze this whole block and then just train the last final portion. and you can see how much am I actually training up the network. So that all of that was just focusing on the definition of the models. But once we actually define a model, we want to be able to train it. And so in order to train it, we need that model definition we were just talking about. We need the loss function saying how good are my predictions? What am I optimizing for? And then we need an optimizer. This can be SGD or Atom. This is basically saying, when I get that feedback from the loss, what do I do with this? How do I optimize my weights? And then you need some training data. And then you also need, you can have validation data and metrics, or you can just say, just only give it training data and you'll only get training results. And then with metrics, it's the same thing. You could just measure your loss, but it's probably useful to actually look at accuracy or some other metric, maybe F1. There's different things that are valuable to you because loss might not tell you anything. The value of 0.7 might not mean anything to you. So you put all these pieces together and then you say, okay, compile my model. So it's packing your model definition and your loss and your optimizer and everything. And then after that, you say model.fit. And then that's when you give it the training data and you say, okay, learn from this now. Give you some inputs, give you some outputs, figure out the mapping between these two. And then here's what a loss curve from that would look like. So I'm going to start with this red dotted line. So this is our training loss. So loss is going down. It's just going down, going down, going down. So this is what we would hope for, is our loss just consistently goes down and keeps getting better, better, better. And then this blue line that's right next to it, this is the validation loss. So this value we also hope goes down, 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 down. But if we have enough parameters in our network, we would expect at a certain point that it starts going up because it's learning so heavily from the training data, it starts learning things that aren't actual true patterns that hold to the validation set. And the other thing that they're measuring here are the accuracies. So we have the losses that are going down, and then we have the accuracies that are going up. So this other dotted line is the red accuracy for the training set. And then this is the blue is the validation accuracy. So you can see both of them go up and they get to, I don't know, 90% or something like that. So we can see that our model converged pretty well. Was there a question online?
Yeah, I'm sorry, this is Stephen again. Question, can you go back to the Keras output? Yeah, just there. I did a quick calculation. So on that dense layer, it says the number of parameters are 235,500. But if you multiply 784 by 300, you come out with 500 less. The multiplication equals 235 by 200. Do you have any intuition where that, sorry, it's 300 difference, where that 300 difference is coming from?
Yeah, so this is, we have two different pieces of that. So you captured the weights part. So the weights is the 784 times 300.
Oh, is this the offset?
The missing part is the 300 for the bias. Yeah.
Yep. Okay, got it. Yep.
Yeah.
Thanks.
Yeah, good question. Okay. So we have the whole setup now. So that was all using sequential. And so I teased it before. The issue with sequential is you don't always have a setup that is as simple as this layer, then that layer, then that layer, then that layer. You might have something where you have sort of branching paths, or you have multiple inputs and you want to handle them in different ways. So you have two things happening in parallel. So that's the advantage of the functional API. So the whole focus of this is basically being, I can define layers and then piece them together however I want. So in this, what they're showing is the functional API where they say, okay, we have two different inputs. One of them is going to have shape 5. One of them is going to have shape 6. And then they have some normalization in here. We'll skip over that for now. And then we also have some dense layers. And so this is the way that this works that's slightly different. The previous one, we just said this layer, then add that layer, then add that layer, then add that layer. In this, what we're doing is we're actually saying this layer takes in this certain input. And so we can reuse things, we can pass them into other pieces. So if we look at this, we're saying make a dense 30 unit layer, and we're going to pass it this norm deep value. So that came from this input deep, and then it went through the norm deep, and then it becomes this value. So it's a little bit tricky to piece through all of the different layers, and we have a separate branch that is taking it more directly. So this diagram makes it a little bit more clear. So this is exactly the problem that the functional API is trying to solve, is basically we have these two inputs side by side. One of them is input wide, one of them is input deep. One of them is we want it to go through a normalization layer. One of them we want to go through a normalization layer, then to a hidden one, then to hidden two, and then we want to concatenate these. We want to put these back together, and then we want to make an output layer. So we haven't talked about why you might want to do this, but just understand this gives you a lot more flexibility, because in the previous setup, you would be limited to just saying this layer, that layer, that layer, that layer, all the way to the end. You can't do this thing where you have two things side by side. Talking a little bit about why that's useful, you might have multiple inputs, and you might also have multiple outputs, and you might have different kinds of layers, and you might have, we talked about like residual connections. You might say like, actually, I want to skip this around this other layer that's doing some operation. So this is the common way to do things now. You can sometimes define simple things with the sequential API, but most of the time you're going to want to use the functional, or the one that we're going to talk about after this, because it gives you a lot more flexibility. You have to write a little bit more code, but it's generally worth it because you get a lot more flexibility. So this final setup.
Ryan,
Yeah, go ahead.
just one question, sorry about that. I want to understand, why do we have a concatenation layer and why is it used?
So
The
the concatenation is combining these two different branches. So in this case, they didn't really justify why do we need two different branches in order to do this. But concatenate is a pretty common operation. You say, I want these models to, or these features to be processed in some way. So like, say I'm trying to combine images and audio and tabular, and I say process these all in a different way, and then at the end I want them to produce vectors and combine them in some way. And so a common way is just to concatenate them, just put them side by side and say, here's my combination of all of these features now. So you could average them, or you could concatenate them and just say each of these get their own output neurons that we put side by side, and then they get processed again in some other way.
And just a quick note. So again, we talked about Keras does a lot of the bookkeeping for you. So if on the left you had, 32 features, and on the right you had another 32 features, you and I look at it and we know that it's 64 when you combine. But remember, Keras is doing all this bookkeeping for you behind the scenes. So you need an explicit concat layer that just simply says, hey, stick the two together, and then Keras knows that, oh, okay, now I have 64. So it's not really doing anything fancy, but it is necessary for you to be explicit anytime you add or remove anything to your data, because otherwise Keras doesn't know to change the numbers for its bookkeeping.
Quick question. Is Keras kind of the industry standard at this point, or?
So at this point, PyTorch has really won out. Like, most models are trained in PyTorch, and there's a new version of this book that's going to come out that replaces Keras and TensorFlow with PyTorch. So Keras is still used, and there's good models that have been released with Keras. Keras is actually, like, at the time this book was written, TensorFlow had kind of consumed Keras. And then at this point, like now, years later, after this book was released, Keras has started supporting PyTorch again because PyTorch has won so much that like people like this interface, but they want PyTorch under the hood.
Yeah, and Ryan and I debated how best to cover this topic. And so in the end, we decided that we'll follow the book just to keep things simple. And really the concepts in Keras and in PyTorch have largely converged, where if anything was easier to do in Keras, then PyTorch just copied it and imitated it. And if anything was easier to do in PyTorch, they just copied it, right? So at this point, it really doesn't matter. I'm someone who can learn like the syntax for new languages fairly well. So like it's a little easier for me. But the good news is now you have ChatGPT. And so if you're just like, hey, I know how to do this in Keras, but I happen to be using PyTorch. How do I do this exact same thing? You're probably going to get a 99.9% accurate answer if you know one and it just tells you what to do with the other one. There's like one little tiny exception with PyTorch where you have to write a for loop. But other than that, everything is pretty much interchangeable, just some slightly different syntax. Okay. So we decided it's going to be easiest if we just cover the book chapter as is. I was planning at the very end of today just adding a couple comments about how PyTorch differs. But what Ryan said at the beginning, if you learn those concepts that he showed, those concepts are exactly the same in PyTorch. And so you will have learned all the concepts you need no matter which you're using.
Yeah, online.
Tim, did you have a question? You can go ahead and ask. All right. If you're trying, we can't hear you. I don't know if you have a problem with your mic.
All right. So moving on to the. Go ahead.
Oh, sorry, I was having some problem with my mic. So I have a question regarding to this 1014, yes, this figure. So it looks like to me, this is more like a nested model, which is like one model inside another model, right? So is there any way, different way that we can create nested model? Just like in terms of how you code it, instead of what we have to build each pieces individually and connecting to one model. Or my question is like, can you have one model inside another model? Are Keras or PyTorch able to handle that situation?
Yeah, that's a good question. So that's exactly what the next section kind of leads towards. It doesn't explicitly say that, but that's a very common setup. So like what people have figured out with like vision systems, they say, oh, someone trained this model to do this really great vision thing. Now I want to take it and I want to just like convert it to some other task. And what they'll do is they'll basically say, okay, my new model is actually just this model plus an extra layer or something like that, or plus some other branch of something that combines into it. So that's a very common thing that people do, and that's what people use this subclassing for pretty commonly. So like in this setup, the way that all of these are defined, it's saying this is a layer, do all of this stuff. But what you could do is say, instead of having a layer, just say, this is my vision backbone, and that vision backbone is actually 32 layers that I'm just calling as one individual block that I'm putting inside of my other model.
Yeah, and just super briefly, said another way on a more technical level, an entire neural network model is actually just a subclass of layer. So if somebody else said, I have this fancy model, you can just treat it the same way as any other layer, just as a piece inside of your bigger model.
Yeah.
Can I ask a question? Yeah. So you were mentioning PyTorch. Have you had experience with JAX? That's what I'm like seeing around, but I don't have much experience. So could you comment on
I've looked at Jax a decent amount. I haven't really used it that much. It seems like the main value of that is if you're using Google's TPUs, and I haven't used those. So I know that you can use it and people are big fans of it, but it doesn't seem to have gotten that much adoption outside of people working at Google or using their TPUs.
Yeah. So as a side comment, to a large degree now you can just write arbitrary Python code and work with Keras and TensorFlow. It has always been the case with PyTorch that you can write arbitrary Python code anywhere you want and it will work. My understanding is with JAX, that's discouraged. And so you want to try and stay within the functions that JAX actually supports instead of just arbitrarily saying, well, I'm just going to add these two things because I know how to use plus in Python or whatever. And if you stick with that, then what Ryan's saying is accurate, that the JAX compiler can write some very, very fast code for running on those TPUs. Um, but it is a little bit more restrictive. You're not technically restricted because you can write Python, but if you do, then you might sacrifice that speed up because the benefit of JAX is that it compiles really fast.
So getting into the subclassing now. So the way that this works and the way that I like conceptualize this is we define our model as this class. And so now we have this single bundle that says, here is our model and here's how we pass through all of the layers. And so I mentally split it into the two different pieces. So the init is basically saying, here's all of the layers, here's all my building blocks. And then the call is, how do I connect them? This goes into this, and that is concatenated to that. And so the way that I think about this, init is saying, okay, here's all my pieces. And then call is saying, how do I put them together? And so now you have this single class that defines both of those together. And so with this subclass setup, like I was saying, you can define all your layers, but you could even define this as like someone else's model. So someone else's model is just a layer inside of my model, basically. And then when I want to use it inside of call, I can say basically, okay, take my inputs, pass it to this layer or someone else's model or something like that. And as long as it's regular Keras stuff, TensorFlow stuff, you can pass through all of these places and then it will figure out what's the path through all of these inputs to the outputs and how am I going to calculate the backprop, the gradient steps in the end. So in this, we have our subclass model saying, here's our wide and deep. We want it to have 30 units is what this argument is saying. And we want it to have ReLU activation function. And then we can define a name and then Keras will keep track of that. And when we save it, we can say, okay, here's my cool model. So yeah, I would, this is my default at this point. At one point, it seemed very counterintuitive because I was used to the Keras setup where you say, okay, just this layer, that layer, stack them all up. But now things have gotten more complicated where you have different branches and you have things that are being recombined and stuff like that. So my default has now become this setup where you say, define all your layers and then put them together. So subclassing is very powerful. It's a little bit more verbose than the other one. So if we look at this is maybe an extra 5 lines of code or something like that over something like this, but it tends to be nice to actually have your whole thing as a single object that you can pass around wherever you want. Doing it loosely like this is a bit more messy. So one of the nice things about Keras 2 is it does the training procedure for you. So you basically say, take my neural network, take my data, and then it does the whole setup for you. So one of the things that you might want is you might want some custom behaviors while it's doing that training. So these callbacks are what can do that for you. So for example, you might want to save your model at every epoch. So every epoch is every time you take a pass of all of your data, basically. So you can define that as one of your training parameters. But you're saying with the model checkpoint, you say, okay, I want this every epoch, or I only want the best one, or I only want the last one, or something like that. So what this will do is it automatically keeps track of all of your training, and then it will say, okay, which one got the best validation loss, or which one was the last. It will just save all of that stuff for you, so you don't have to write the logic for saving your model out. Another very common one is early stopping. So this is basically saying I train my model for 300 epochs, my loss is going down, 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 and then I see my validation losses going back up. I can just continue training it, but I probably want it to stop because I can see it's not getting any better. So you can say with early stopping, after 10 epochs and it hasn't improved, then just kill training and just give me whatever my best checkpoint was. So these are two very common ones. There's other Keras callbacks that are built in. But the other thing that you can do with this is it just follows some sort of template, and you can define what the behaviors are. So you can write your own callback and you say, I want this callback to be triggered at the end of every batch, or at the end of every epoch, or at the beginning of an epoch, or only once the full training finishes, or something like that. So these callbacks, there's a template for them, and you can basically say, fill out the details, and then whatever Python code you want, you can place in there. So they touched on TensorBoard. I won't talk about it too much because people use it, but it's not that common anymore. So TensorBoard is this tool where you can basically say, during my training procedure, write out a whole bunch of logs and then help me visualize them. So like up here, they made this custom graph. They said, okay, here's my training loss, here's my validation loss, here's my accuracy, and then they said, plot this myself, write some code, make some plotting. But the nice thing about TensorBoard is you basically just say, send data to this hub and then plot it however I want in this nice UI. So if you want to say, okay, plot this number versus that number, or add some smoothing to it or something, it's very useful to be able to visualize your training runs. So TensorBoard is not that common anymore. There are certain like experiment tracking platforms. The one that I use at this point is called Weights and Biases, and it functions very similar to TensorBoard, but it's a hosted service. So I can basically just say, send this to wherever, send it to their server, and then just log as many metrics as I want. So I have all of these things set up here, so you can see my training loss going down and stuff like that, and I can customize how these are visualized and stuff like that. So if I want to smooth the graph, I can do something like that. If I only want to look after the 1000th step or something like that, I can do just about whatever I want. And the nice thing about this is that it's free up until 5 gigabytes or something like that. But in reality, when you're just sending simple time series data points, it hardly takes any space. So I've been on the free account for basically forever. Yeah, and there's different ones. There's Neptune and other ones. That's just the one I use. So if you see other people using other stuff, there's plenty of valid options. That's the one that I like though. So earlier we talked about some hyperparameter tuning stuff. So how many layers, how many neurons, that stuff. One of the things that they pointed out was the Keras tuner library. So this is a library where you take your neural network setup and then you basically say, run it a bunch of times and try the different options and then see what does the best. And so you can use very naive approaches of basically saying, just like set these values to random numbers and see what does best, or you can do something a little bit more intelligent, saying like, be very systematic and go across a range of possible values. or people have gotten very fancy and they've done Bayesian optimization and Gaussian processes and evolutionary algorithm stuff. In practice, you don't do this very often because it's pretty expensive to run. If you're doing like 100 training iterations and trying to squeeze out the last possible run, that can take hours, days, weeks, depending on the size of your data, the size of your network, all of that stuff. So it does get done. It's not that common. One of the things that I see on Kaggle all the time, there's people that they say, okay, I do my Optuna, my hyperparameter optimizing runs, and then it ran for 12 hours, and then I get to the end, and these are the great like hyperparameters. I use that, and then I go take it to the leaderboard, and it doesn't do any better. Maybe it does better, but not consistently or something like that. So there's definitely bounds where you go outside of it and you get catastrophically worse performance, but in general, it's pretty difficult to like significantly improve your performance. Typically, the way that these things work is like more data, bigger network just wins. So if you have enough data to actually saturate things, you just go bigger, bigger, bigger. It's not like some difficult, like I need to find the value 0.12734. Like people optimize those things too far, and then it really doesn't get them any significant gains. So this is one of those things where they pointed out Keras Tuner, but there's a bunch of other popular ones too, but I wouldn't really worry about them too much. I think they're useful to learn about, but they're in general not that valuable. So talking about the model dimensions a little bit, we've already touched on this because people ask questions about it, but I would say the sort of general rule of thumb is just start at some semi-reasonable value. So 100, 512, something like that, and then just run training and see how it does. If you want more performance, you can say, okay, try making this bigger. How does that make the loss curves change? Does this seem better? Does it seem worse? And then you can fiddle with it from there. In reality, it's not typically the driving factor. Most people, when they're training a model like this, they don't have enough data to really get like the value out of something like that. So yeah, I wanted to show a few things outside of the book. So I showed the weights and biases. This is one that I highly endorse. It's a good way to track your results. I would say like I've done a lot of Kaggle competitions, and I think the inflection point for me getting like much better at competing was introducing these experiment tracking tools, because it made it much easier to compare results. One of the things was when I was just using raw Keras and not plotting my results, it was difficult to like go and see how is this training run doing versus that training run. How do I get feedback? And you can tell a lot of things just from the way a graph is progressing. You don't need the value all the way at the end. Sometimes you can say, oh, look, this one's getting so much better validation loss, only one epoch in is probably better in some way. So this gives you a lot of feedback to be able to visualize and not just look at the raw numbers of what you have going on. So that's one thing that I highly recommend. So in the chapter, they showed the Keras tuner. I wanted to point out this Optuna one. This has become very popular. So this is a hyperparameter optimization library that a lot of people like because it's very generic. You can basically say it doesn't matter if it's Keras or PyTorch or some other random optimization problem. So it's a very useful library to know about if you ever run into one of those problems. And then the last piece that I want to show, Andre Karpathy is a very popular researcher who he was just on some big podcasts recently, but he's known for being a phenomenal teacher. And so one of his videos that he made is showing basically the nuts and bolts of neural networks and how backpropagation works. And so it's a long video, it's 2.5 hours, but it's one of those things where if you watch this end to end and you follow along, you'll have a much better intuition of what's actually happening with all of the shapes and everything here. So like before there were some questions about like how does this shape map to that shape and how do these neurons go to that neuron or go to those neurons. And so this is a very good video going in depth of like how all of these things are connected together. So highly recommend that video. Question? Yeah.
Yeah, you're going to include all those links in the YouTube video description, right?
Yeah. I'll put these links in the notes.
Okay, and another thing I had was just like sorry, I don't get your name. Like just like how we said like about the image thing. So instead of flattening it, uh doesn't Python or sorry what the PyTorch or Keras or TensorFlow, don't they have a slicing technique where it kind of like slices layer by layer and then you kind of like that's more better than a flattening approach, right? So
Yeah.
what?
So in the later chapters, we'll look at some of the different, they have specific layers that are actually good for images and stuff like that. So
Okay.
yeah.
Oh, okay, got it. So, thank you.
Yeah. We started with just the here's how you make a neural network, and then we'll figure out in the later chapters how to actually make it good.
Okay, thank you.
Yeah. And one final thing. So when I was first starting, one of the first things that I made was this animation, and it's basically going through this sort of MLP setup. And so I did this little project where I drew some squares and triangles and circles, and it kind of followed along with the fashion MNIST style thing. And so I drew these simple shapes, and then I showed the neural network diagram saying, here's my inputs, here's my outputs. And so this is just throwback to when I was first starting. This was something that I made, and it's been around for so long that it has like a whole bunch of views now. And it's not my proudest work because it was when I was first starting, but I just wanted to point out like here's a diagram of a neural network that I made a long time ago. And so this is trying to classify triangles, squares, circles, very similar to what they're showing in the example for the Keras stuff.
Have you gotten any better at drawing circles?
No, my writing has definitely gotten worse actually. So yeah. All right. Well, that's all I have. Open for any questions.
Yeah, I had one other question. So it's regarding the transformation that's been applied to the input and output on the multi-layer. So there, the step function and the sigma, like basically that's the same for all the multiple layers, or it's just is it the same for the hidden layer and the output layer?
It can be different at different points. So you could say at this point I want a sigmoid, and at this point I want a ReLU. So you can change it throughout the network, but in reality, most people just say, I like ReLU everywhere. So the typical setup that I would say, like the default is people have their input and then they have their hidden layer, and their hidden layer will have ReLU, and then however many hidden layers with ReLU. And then at the end, they'll have their output, and their output has whatever activation function is relevant to their problem. So if it's binary classification, then they do sigmoid, or if they have multiple, then they do softmax. So I would say ReLU is safe default. You can just assume that's most places.
Okay, thank you.
Yeah, I think I had a comment that I put in the chat, but just to clarify, like in my mental model, we use the same terminology and the code is the same, but when you have an activation function on your output layer, it's not really acting in the way the other ones are. The way the other ones are acting is it's introducing a nonlinearity so that your model can learn very interesting complex features. Okay. The activation on your output layer is really just formatting your final output. So if you think of that one as your output formatter instead of as an activation, then it makes sense that people are just like, well, I use whatever. I use ReLU everywhere. But then you're like, but why do you have something different on your output? You're like, well, I'm doing binary classification. I want a number between 0 and 1. And so I have a formatter function that just takes my output and it turns it into a number between 0 and 1. So that's the mental model I have as to why they're all the same except for the output layer. Because the output layer, it's really defined by what is the range of your particular problem. Any other last questions? All right, so super quick note. The next couple chapters, we're going to talk a little bit more about training. And in particular, one of the questions was, how do you deal with overfitting? We're not going to cover every single possible thing we do, but we're going to cover some of the basics for neural networks. And then I think 3 chapters from now, we're going to have a series of 3-4 chapters that are talking about different neural network architectures. So we have only talked about these dense layers where it just takes a combination of every single possible input from the previous layer. We're going to talk about some different ways that people have arranged things and whatnot. And in particular, if you guys, any of you heard of convolutional layers, CNNs for vision, you've probably heard about transformers. So we're going to get into some of those other details in the remaining chapters in this part. So it's more just about generic processes around training, and then we get into specific different architectures. So that's the roadmap for this part 2, which is, I don't know, around 9 chapters or something like that. As far as the timing, because I actually have a bunch of travel and stuff in November, I'm actually not sure when all the chapters are going to happen. Next week is going to be the monthly event. And then it's possible that the next chapter, which is chapter 11, it might not even be till December. We might have some other topics. So that was not the original plan, but it just might turn out that that's how it works out. So please stay tuned, check on Meetup for the event notices. And in the meantime, if we're not able to talk about chapter 11, Ryan's looking into other interesting topics that we can do on Saturdays until we get back to doing the book. So just administratively, just letting you guys know the schedule in November might be a little bit up and down. All right, looks like one more question online. Jock?
Do we have another question online?
Yes, question. So you mentioned that there is a different, because we're going to cover TensorFlow, we're going to Keras, and we're covering PyTorch, but that was in the new version of this. Is there anything that we can kind of read up on to prepare us for that, in a sense that the things that's not covered in this book about the upcoming, I guess, different version that we can kind of like look at to prepare ourselves?
So the new book is coming out soon. I don't think it's fully out yet. I'd have to double check on that. I think it's, if you have the O'Reilly subscription, I think you can actually get a copy of it already. But I do know that the notebooks are available for the new version. So there's code that's already out there for the PyTorch version of this. So if you want to, you can go kind of side by side and say, compare the PyTorch version versus the Keras TensorFlow version.
Or is there another website or something else we can use? This might dumb it down a little bit more for people who are familiar.
I'll see if I can find that version, and I can send you some links.
Yeah, I haven't checked the correspondence, but chapter 10 in the new PyTorch book and chapter 10 in this book, I think are probably going to overlap a lot. So if you look at the chapter 10 sample notebook for the new PyTorch book, I think that'll be very useful. The main difference that you're going to run into, again, it's going to be some slight syntax differences between the sequential, the functional, and the subclassing, but the concepts will be identical, basically. The main difference is that in Keras, you just write one line and you say fit, and it'll train your neural network. In PyTorch, you write a for loop and you explicitly tell it the steps that you want to do. So when you're first learning, that's a little bit more work because you have to have like a minimum of 6 lines or something like that in this for loop. Later on, it ends up being a lot more convenient because like in this chapter where they say, hey, you can write these callbacks. So at the end of each epoch, you can say, I want to, save a copy of my model, whatever. Well, when you wrote the for loop, you just put a line after the end of at the end of the for loop that says save my model. You don't have to do a callback. You don't have to do it. Everything is just explicitly there right in front of you. So early days, that's what people loved about PyTorch was like, I'm a researcher. I want to do one thing different, and I don't want to have to jump through all these hoops. And even like Keras 1.0 didn't have callbacks that came later. So when they saw that, people want to do all these things. So it is possible to do them now, but other than having to write that one little for loop, mostly everything is just like, replace this whatever ABC with an XYZ, and then voila, you've switched between the two.
I can show for just a second. So I do most of my stuff in PyTorch, and I can show how this is very similar to the stuff that we looked at. So my setup is a little bit more complicated, but it's very similar. And I'm making a class. This is my model. In the Keras setup, they had a specific like Keras dot whatever they inherited. I'm doing nn.module. In PyTorch, everything's just nn module. And then it's the same setup of your init is basically just saying define all my layers, define the building blocks that I want to work with. And then in my setup, forward is where we define like here's how you use the model. So forward is going to say I defined all these layers, now put it together in this way. So it functions exactly the same as Keras TensorFlow. It might have slightly different names for layers, and it might have different modules that you have to inherit, but it's very, very similar. So can show a little bit of PyTorch, but it's really like, unless you start digging into the specific, like this layer is named dense instead of linear, it's not that different. All right. Thank you, everyone.